section 4.5, Exponential Growth and Decay, Modeling Data. Now, what we're going to see here are some applications of all the exponential things and logarithmic things that we have been dealing with. The main application, really, of exponentials are for things that experience exponential growth or exponential decay. So exponential growth, those are things that start growing. They usually start very slowly. They start growing like this, and then they just shoot up. Okay, that was exponential growth. We see this a lot in the growth of bacteria, or in today's world, the spread of the coronavirus. If one person gets it and they spread it to 2 people, then 2 people each spread it to 2 people, and it keeps going and going and going, and then eventually it shoots way up. Okay? And we see this whenever exponential growth and decay, they both have basically the same formula in the beginning. Okay, let me just talk through this. A is the amount of whatever it is that you have at the time t. So t is time. A naught is the amount of the substance, bacteria, whatever it happens to be, at time 0. So this is your initial amount. E is, of course, E. Now, K is the constant that takes care of whatever world we are dealing with. Bacteria grow at a set rate, so if we know that, then that's our K value. It just depends on the specifics of what we're doing. Now, whether you have exponential growth or exponential decay depends on your K value. If your K is positive, then it shoots up. Okay? If your K is negative, this is the one that goes like this. It starts decaying really fast, and then it starts to slow down. Now, where we see exponential decay a whole lot is when we're talking about radioactive materials, specifically carbon-14. You hear about radiocarbon dating. We know that the amount of carbon-14, which is radioactive, you half the amount. It's a set amount of time. So that's where you see exponential decay a whole lot. We are going to be working problems with all of these. I'm just going to be giving you a lot of information in the beginning, and I promise you will see how all of this fits together. Okay, now let's say we do have growth of bacteria. Okay, so they start growing, they start multiplying, they're growing really, really fast. When you're talking about just a plain old exponential model, there's no reasonable limit. I mean, this assumes if it's bacterial growth that they have no problems finding new hosts, they have no problems finding fuel, they have everything that they need in order to live. Now, we know that that is not reasonable. There's always a limit as to how big a population can get, okay? Because they will run out of resources, they'll run out of food, they'll run out of water, they'll run out of something. And then the logistic growth model is the one that helps take care of that. So these are slightly different. This is mainly like what you would use for predictions. And here's where you have a little bit more information and you know how the largest this thing could possibly be. And you have these 2 models, okay? And you can see that you have A, E to the negative BT. Here we have an A, E, and then K is a decaying entity because it's negative right here. Okay, so we have these particular formulas. Now, if you look at this, as time increases, so as we get larger and larger and larger times, this part, A equals B to the negative T, approaches 0. And that's because once this, remember this, if it's a negative exponent, it's taking this value A e to the bt and moving it into the denominator. And if the denominator is getting larger and larger and larger and larger, then your fraction is getting smaller and smaller and smaller and smaller. So as this part approaches as time approaches infinity, this part right here goes to 0. And that means you essentially have C over 1. So your overall A value gets closer to C. Y equal to C is a horizontal asymptote of the graph, okay? And so the value of A can never be larger than C, and C represents the limiting size that A can attain. Now, I know that's a lot of information. I just threw at you at once. Basically, what this is saying is if you have a problem that's in this basic form and they ask you, what is the maximum number of bacteria available here or whatever, you're just going to say that top number, whatever it is. That's your answer. That's as big as it can possibly be. Okay, now one more little thing. Expressing an exponential model in base E. So in the real world, you start setting up a model so that you can make predictions on the data you have, and you may find that an exponential function works really well, but it may work really well with logarithm or exponent like base 2. And we know that base 2 is not very friendly for our calculators, and most of the time we want base 10 for a common log or base E for a natural log, okay? Because that's what our calculators, that's what it's capable of. And so often you'll have a form, an exponential in this sort of form, where you just have a general base and it doesn't have to be one of the ones we really like. This formula will allow you to change your base, okay? If you look right here, we have E raised to the natural log. We know that those have the same base, and so you would just get the B to the X. Okay. So let's try working a couple of problems. So an artifact originally had 10 grams of carbon, 14 present. The decay model looks like A equal to 16 times E to the negative 0.000121 T. And this describes the amount of carbon-14 present after T years. We want to round to the whole number and we're going to calculate these things. Now, before we go on, when you are doing your homework, this is incredibly difficult to see because the print is very, very, very small. So just in case, if you don't know how to enlarge the font on a web page, if you're using a Windows or a PC, you hit Control and plus to zoom, and then Control minus to reduce the size. And then it's basically the same with a Mac, but it's Command. Command plus and Command minus. I strongly suggest that you zoom in, you really enlarge the font when you're doing this homework, because you'll have like really long decimal numbers up here with a bunch of zeros, and it can really cause you problems just because of the way it looks. Okay, so let's start working a problem. How many grams of carbon-14 will be present in 5,715 years? Well, this is our time. So we plug in this number right up here. So I have A is equal to 16 E to the negative 0.000121 times 5715. Okay, so let's plug this into our calculators, and we're supposed to round to the nearest whole number, right? Okay, so let's see what we have. I have 16 times E, that's not right, 16E, to the, I'm going to put these in parentheses, negative 0.000121 times 5715. Close parentheses, hit enter, and it appears to be about 8 grams. So we got, I'm going to write out more decimal places. Okay, so it's about that, so approximately 8 grams. We'll have we started off, had 16, and it will have about 8 in this many years. Okay, so this is, we essentially halved this. So this is almost the half-life. Okay, now how many grams of carbon-14 will be present in 11,430 years? Okay, so let's plug in that value. It's going to be worked essentially the same as this, it's just our time value will change. So 11,430. So 16 E to the negative 0.000121 times 11430 is about 4. So our A is about, let's see, it's 4.013 or about 4 grams. Okay, now radioactive decay, once you know the half-life, that stays the same. So right here, I mentioned half-life, we had 16, we went down to about 8 in 5,715 years. Now the amount, that's the half-life. So it's going to take another 5,715 years to reduce this in half. We went from 8 to 4. Now, so my question is, just to double check myself, I noticed this. Is this value twice this value? I plugged it into my calculator, and you can see that it is. Okay. Now, since we had rounded right here, if it wasn't exactly 2 times that, I wouldn't have been concerned, but it was a very nice little check.